So in this video you will be learning about permutations and combinations. Some of you may be somewhat familiar with it from a previous class, but I think that through your work and the different problems that we've done, you've come to have a better understanding of where some of these formulas that you did know or are going to be presented in this video are coming from. So we're going to start off by looking at an example similar to what we've seen in class already. So the first example, we have 8 students in my PLT. I need to choose the officers, president, secretary, and treasurer. How many different sets of officers can I have? Well, if we start off with the president, we have 8 choices for president. But if one of those students is chosen for president, he or she cannot be chosen for secretary. So if student number 4 was chosen as president, for secretary we only have 1, 2, 3, 5, 6, 7, and 8. In other words, there are 7 choices for secretary. And I only drew it part of the tree diagram there. Of course, we would also have 7 branches coming if student 1 was president, or student 2, or student 3. So we would have 8 different groups of 7 for president and secretary. Then if we had the treasurer, of course, if student 4 was president and student 8 was secretary, we only have students 1, 2, 3, 5, 6, and 7 left to be chosen for treasurer. But again, we could do that for each of the 8 groups of 7 that we had in the first 2 officers. So that we know that the shortcut for this is to use the fundamental counting principle. 8 choices for president. For each of those 8, there are 7 choices for secretary, for a total of 56 possible choices for president and secretary. And then for each of those 56, there are 6 choices for treasurer. So 8 times 7 times 6, which is 336. So that's our answer. We have 336 different sets of officers in this example. Hopefully you would have been able to figure that one out fairly easily. Let's make it a little more complicated. Let's say we're same situation, but this time we're going to send all the officers to an all-expenses-paid trip to Punta Cana. How many different groups could I send to Punta Cana? Now this time I don't care about who's president, who's secretary, or who's treasurer. Why? Because the hotel doesn't care. The bus company or plane company doesn't care. All they care is who are the people who are going. They don't care what their title is. So if we had student 8 was president, student 1 was secretary, and student 7 was treasurer, well, as far as the bus company is concerned, that's the same as if 7 was secretary and 1 was treasurer, or this order, or this order, or this order, or this order. So there are 6 different ways to arrange student 8, 1, and 7. As far as the bus company or hotel is concerned, those are all the same. The order does not matter. So all 6 of those we can count as one group. We can call the group whatever. Let's call it 817. We could have called it 187. Doesn't matter. So we know that that group consists of 6 different orders. We could do the same thing for 1, 2, and 3. Or that can be the same as 1, 3, 2, 2, 1, 3, etc. Again, we have 6 different ways of arranging student 1, student 2, and student 3. So those will all go into one group, which we can label 1, 2, 3. So the question really is, how many groups of 6 are there? 817 is a group of 6. 1, 2, 3 is a group of 6. How many groups of 6 are there out of those 336 different sets of officers? Well, how many groups of 6 are there in 336? Simple division. 336 divided by 6 is 56. So there are 56 different groups of 3. Okay, so that's the answer to the question. How many different groups can I send to Punta Cana? There are 56 different groups we could send to Punta Cana. Well, that's all nice, but what if I had an absurd number of students? What if I had 200 students that needed to choose 10 officers? Same Same situation, but this time more students and more officers. So president, maybe we have a vice president, maybe we have the Secretary of Defense and the Secretary of State and the, whatever. We have 10 different officers to choose. So I'm not going to draw the tree diagram, but we know we have 200 choices for the first officer and then 199 for the second. And so we're going to multiply them because for each of those 200 choices of the first officer, we have 199 of the second. 198 for the third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th. So how many is that? Well, that's just a really big number. Let's not worry about how big of a number that is. We just know that's how we get it. I'm more interested in how we get things than what the actual answer is. So if you remember about factorial, well, 200 factorial looks similar to this, but a little bit different, right? Because 200 factorial keeps going, looks the same, looks the same, looks the same, but it keeps going all the way down to 1. So maybe this is helpful if we could get rid of the ones that we don't want. Well, we don't want the 190, so we can get rid of it by dividing by 190. We don't want the 189. We can get rid of it by dividing by 189. And we can keep doing this, divide by 188, 187, all the way down to 1. So what did we actually do? We just did 200 factorial, but we divided it by 190 factorial, canceling out 190, 189, 188, 187, all the way down to 1. And what we're left with is exactly what we wanted. Why would we do this? It's just a faster way of writing it. 200 factorial divided by 190 factorial is easier to write than 200 times 199 times 198, etc., etc., etc. So our answer to this question is this. Could you find out what that is? Maybe if you had a super duper calculator, but I couldn't even find the answer to that on the internet when I Googled it. It's a really humongous number. All right? You could do it the long way and do 200 times 199 times 198, etc., and you'd probably be able to do that in a regular in a regular calculator. I didn't do that. Okay, so let's move on. Again, same example, 200 students, 10 officers, all expenses paid, trip to Punta Cana this time. So in this time, order doesn't matter, right? The hotel doesn't care what the titles of these officers are. They just want to know which rooms to book. So remember, we had 200 factorial divided by 190 factorial, total different sets, different groups of 3. Different groups of 10. So, but we know that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is the same thing as 1, 2, 3, 4, 5, 6, 7, 8, 10, 9, which is the same thing as 1, 2, 3, 4, 5, 6, 7, 10, 8, 9, as far as the hotel is concerned. And we could keep finding all of those combinations. That would take a really long time to list them all out. Luckily, we know of a shortcut. Right? So in that first slot, there are 10 different to choose from. In the second slot, 9 different to choose from. So if students 1 through 10 are chosen, how many different ways can we arrange them? 10 times 9 times 8, etc. All the way down till we only have one option left for that first student. So there are 10 factorial different ways to choose that. 10 factorial different ways to arrange those 10 students. Alright, so how many groups of 10 factorial are there? Again, it's just a simple division. So that's how many total different groups we had, but we know that we can group them into 10 factorial. How many of those do we have within that? That's our answer. What is that? I don't know. You can figure it out. But it's 200 factorial divided by 190 factorial for how many different sets we have, and then we have to divide that by 10 factorial because 10 factorial can be grouped together. Okay. So let's try to sum up what we just did because it's a little bit confusing. So sometimes order matters. We know there are lots of ways when order matters, or lots of ways to arrange or choose the different sets. These are called permutations. That's the mathematical word. Permutations, order matters. So in the first example, we had 8 students and we chose 3. So the notation we would use is P parentheses 8 comma 3. That means permutation where we have 8 of something and we're choosing 3 of them. Permutations tells us that order matters, so we do 8 factorial divided by 5 factorial. In other words, 8 times 7 times 6, which got us our 336. In example 2, we had 200 students, we were choosing 10, so that would be P parentheses 210. So we have 200 choosing 10, and we're doing permutations here because order matters. And our answer was 200 factorial divided by 190 factorial. When order does not matter, we know there are going to be fewer ways, right? Because the different orders can really be combined into one group. That's combinations. So in our first example, we had 8 students and we were choosing 3, but order did not matter. So that's C for combinations, 8 comma 3. And those were our permutations, and we had to divide that by 6, or 3 factorial, because those are the different ways our 3 officers could have been arranged. In example 2, 200 students choose 10. C 200 comma 10. Those are our permutations, but we need to divide that by 10 factorial because that's the number of ways our 10 officers could have been arranged. So how do I remember which is permutation and which is combination? So one way to remember, the way I remember, is I think of a combination lock as being a terrible name, because in a combination lock, order matters. You can't put the right numbers in a different order and have the lock open for you. So it really should be called a permutation lock. Combination lock? No way. It is a permutation lock. That's how I remember. In a permutation, order matters. Combination, order does not.